Okay, so let's start then. Okay. So, yeah, I just wanted to say a couple of things about the induced connection on the dual bundle. So, I did say that we could define it in terms of the covariant derivative along curves, right? So, for that, remember the picture we had was if you had a point, say, P equal to gamma 0 and Q equal to gamma t. So you're given a point P and you're given a tangent vector V at P, and you take a curve gamma whose tangent vector at P is equal to V. So then you have the fiber EP over P and the fiber EQ over Q. And you have the parallel transport map, let me call it P sub T, from EP to EQ. Now, if you take duals, then you have the fiber of the dual bundle, EP star over P and EQ star over Q. And the dual of the parallel transport map goes backwards. PT star goes from EQ star to EP star. And then we can define, so given say alpha is a section of the dual bundle and a point P in M and a vector V in TPM. You choose gamma curve such that gamma 0 is P, gamma prime 0 is V, and then you define, so we directly define the connection acting on alpha via the vector V. So nabla V of alpha, you define this to be the limit t tends to 0. So you take alpha at the point gamma t. Right, now this is a point in the fiber EQ star. So if I apply PT star to this, then that will give me a point in the fiber EP star. From this, I can subtract alpha at P. And then I divide by T and let T tend to 0, right? So this will be an element of EP star. Okay. So then the claim was that this satisfies the Leibniz rule. Okay. That is, if S is a section of E, okay, then and say X is a vector field on M, such that X at P is equal to V, then if I look at alpha at gamma T applied to S at gamma T, right? And if I differentiate this with respect to T at T equal to 0, then I'll get X applied to alpha composed with S, right? Alpha composed with S is a function on M. So I can apply my vector field X to that function on M, right? That I'll get by differentiating this function of T. This is a scalar function of T. Okay. Now, how do I compute this derivative? So I can use first order Taylor expansions. So remember, for a section of a vector bundle with a connection, if I looked at the section along a curve, then I had this first order Taylor expansion. S at the point gamma t, I can write as pt of S at P plus T times nabla x S at P, right? Plus little o of T. Yes? We had this first order Taylor expansion, right? Yes? Yes, is that okay?
Yes, that is fine.
Now, what is alpha composed with PT? By definition, that is PT star acting on alpha, right? Yes, by definition of the dual linear map, alpha composed with PT is PT star acting on alpha of gamma T, right?
Yeah, right.
This is by definition of the dual, okay? So then I get S at P inside plus T nabla x S at P plus little o of T. Yeah. But now what is PT star acting on alpha of gamma T? If I look at the definition of this connection on the dual bundle, this is going to be given by, so remember PT star at alpha of gamma T, this is a vector in the fiber EP star, right? So in that fiber, I can write it as alpha P plus T nabla x alpha at P plus little o of T, right? By this definition here. Yes?
Yes, sir.
Right? It just follows directly from the definition. Now I have a linear functional acting on a vector, and so the pairing between linear functionals and vectors is bilinear. So I can expand this out, right? And when I expand this out, the first term will be what? Alpha composed with S at P, right? Plus I'll get a term in T. So that term will be nabla x alpha at P plus nabla xs plus alpha of, so I'll get this alpha acting on this term. So I'll get alpha acting on nabla x s at P, right? That will give me two terms in T. So, well, sorry, I'll get nabla, sorry. So I'll get this nabla x alpha acting on S, right? And that times T. So I'll get nabla x alpha acting on S and that at P. And similarly, I'll get alpha acting on T nabla xs at P. So that will give me another term in T. So I'll get alpha acting on nabla xs at P. So that will give me two terms in T. And then the little o of T and the little o of T acting on all the other terms will give me something which is little o of T, right? Okay. Yeah. So if I take this alpha composed with S at P to the other side, then I'll get, and I divide by T, then that will give me that X acting on alpha composed S at P will be the coefficient of T here, right? So that will be exactly what we said, nabla X alpha acting on S at P plus alpha acting on nabla XS at P. Is this clear? So that's the Leibniz rule for this induced connection. Is it clear?
Yes, sir.
Okay. So yeah. So that's what I said. If you define the connection like this using the dual of the parallel transport, then you'll see it satisfies the Leibniz rule. Okay. It's not difficult. Okay. And so what I'll leave as exercises for you to do is that so exercise. So if nabla is defined on E star. So let me call this equation, this Leibniz rule, say double star, and satisfies double star. And then A for any curve gamma, if capital D dt and let me write it as d tilde dt are the covariant derivatives along gamma for E and E star. Yeah. Then for sections S and alpha of E and E star respectively, along gamma. If I look at alpha composed with S, so that's a function, a scalar function of T, then ddt of this satisfies the Leibniz rule. This is going to be d tilde dt of alpha. So that's a section along of E star along gamma. This applied to S. Okay. Plus alpha T applied to ds dt. Okay. So the covariant derivative along curves satisfies the Leibniz rule if the connection satisfies the Leibniz rule. All right. Okay, so try and prove this. And from this, then it's not hard to show that if P and P tilde are parallel transports, so parallel transport along gamma for E and E star respectively, then P tilde, the parallel transport for E star is P star inverse. Okay. So if you can prove part A, then part B will follow from part A. Okay. Is the exercise clear? Yes?
Yes.
Okay, so try and prove this. Yeah. Okay. All right. So now I want to start talking about Riemannian geometry. Yeah. All right. So this is going to be a very brief introduction to Riemannian geometry. So we've talked about what are smooth manifolds, right? Now, what is a Riemannian manifold? So that means a manifold with an additional structure which will allow us to be able to measure two things: lengths of curves in the manifold and not just lengths of curves, but also angles between curves. Okay. So if I have this manifold, then if I have a curve like this, I should be able to measure its length from the starting point P to the ending point Q. And if I have another curve which intersects it at a point, then I should be able to measure the angle of intersection between these two curves. Right? So in Euclidean space, how do we measure lengths of curves? You integrate the norm of the tangent vector, right? You integrate norm of gamma prime t dt. So this suggests that on a Riemannian manifold, we should have a way to measure norms of tangent vectors, right? That means on each tangent space, we should have a norm. Okay, so each tangent space, TPM, should be a norm vector space. Okay, well, that will allow us to measure lengths of curves, right? As soon as you have a norm on each tangent space, then given a curve gamma, you just integrate norm of gamma prime t dt. That will give you a length of a curve, the length of a curve. But if you want to measure angles between curves, right, then what is the angle between two curves intersecting going to be? That's going to be the angle between their tangent vectors, right? Now, that means on the tangent space, we should have a way of measuring angles between vectors. So now typically in a normed space, it's not that easy to define angles between vectors. However, we can define angles if we have what? When can we define angles in a vector space? What structure do we need?
Inner product, right?
If we have an inner product, right? So this suggests that actually we should have on each tangent space an inner product. Okay. So what we want is actually on each tangent space TPM, we have an inner product. Okay. So, a Riemannian manifold will be a manifold M equipped with what is called a Riemannian metric, that is a choice of inner product on each tangent space. Okay. Which varies smoothly with the point. Okay, so on each tangent space TPM, I will have a inner product G sub P. Okay. Now, what is an inner product on TPM? That means a bilinear function, right? From TPM cross TPM to R. So if you think about it, point-wise, you have a bilinear function on the tangent space. So that means at each point, you have an element of TP star M tensor TP star M, right? Right, the dual space tensor itself, yes? That is the same as the space of bilinear functions on TPM, right? We saw this isomorphism in the beginning. Yes.
Yes.
Right. So now what does it mean? So that means our Riemannian metric will be a section of the tensor product of the cotangent bundle with itself, right? And this will be, whenever I use this notation gamma, I always mean smooth sections. So this will be a smooth section of this bundle, right? Okay. Such that for all P and M, the value of the section at P, GP from TPM cross TPM to R is an inner product. So it satisfies symmetry and positivity. Okay. So is this clear? This is what is a Riemannian metric. Okay. Yes.
Yes.
Okay, so it's a smoothly varying. The fact that this is a smooth section of this bundle means that this inner product varies smoothly with the point, right? It depends smoothly on P. Right? That's what it means to be a smooth section. Okay. So what does this look like in local coordinates? So if I have,
Sir, locally, I mean, is that inner product same as the inner product on Rn if the manifold locally looks like Rn?
no. So locally, what does the inner product look like? So if I have local coordinates, we'll see what the inner product looks like, the dependence on the point. So if I have local coordinates, say phi equal to x1 to xn, right? And so then I have a basis of the tangent space del del x1 up to del del xn. This is my local basis of the tangent bundle, and taking the dual basis, gives me a local basis of the cotangent bundle. So that is dx1 up to dxn, right? This is my basis of TP star m, right? Yes?
Yeah.
Okay. So what is my basis of the cotangent bundle square, tensor product square? That will be dxi tensor dxj, right? Yes? This will be my basis of TP star m tensor with itself, right? Yes?
Yes.
And so what is my G of P going to be? With respect to this basis, this is going to be a sum over ij, right? So remember, when I looked at multilinear functions on a finite dimensional vector space, right? We had the basis for the space of multilinear functions. It was given by tensor products ei1 star tensor up to eik star, right? And the coefficient of this tensor product ei1 star up to eik star was my multilinear function t acting on the tuple of basis vectors ei1 up to eik, right? So in this case, I'll get dxi tensor dxj. This is my ei star tensor ej star. The coefficient of this will be my multilinear function gp acting on ei ej, which is del del xi del del xj, right? Okay. Is this clear?
Yes, sir.
So this is these coefficients, this is gp acting on del del xi del del xj. This is some function of p, right? So I can write this as a function gij. This is normally denoted. This is gij of p dxi tensor dxj. Okay. Okay. So let's write capital G of P is this matrix GIJP. Okay. Yes. Okay. So this is a smooth matrix valued function, right? So G is a smooth map into MNR, right? Yes. Okay. Now, how can I write my inner product little g in terms of the matrix capital G? Well, if I take vectors V, which is say summation Vi del del xi and W equal to some Wj del del xj. Okay, these are in TPM. Then GP of VW will be what? This will be by bilinearity. This will be sum over ij VIWJ GP of del del xi del del xj, right? Yes. So this is sum over ij VIWJ Gij of P, right? Okay. And what is this? This I can write as nothing but the Euclidean inner product between the vectors G, say, let me write it as V tilde and W tilde. This is Euclidean inner product where V tilde is the vector in Rn. My chart d phi, the derivative of the chart applied to V, which is nothing but V1 to Vn. And similarly, W tilde is d phi P of W, which is W1 to Wn. Okay. So in response to your question, what you see is that the inner product G, it is not exactly the Euclidean inner product. It is given by a smoothly varying inner product on Rn. Right. Remember, any inner product on Rn, right, is of the form V tilde W tilde goes to the Euclidean inner product between some positive definite symmetric matrix G into V tilde inner product, Euclidean inner product with W tilde, right? Yes?
Yeah.
Right. Any inner product in Rn is of the form Euclidean inner product between GV tilde and W tilde, right? Got it?
Yeah.
So what happens is when you identify the manifold with Rn locally, what happens is all the tangent spaces are identified with Rn. So my inner product on each tangent space is going to be identified at each point with an inner product on Rn. Now that inner product on Rn is going to vary smoothly with respect to the point. So therefore, it's going to be given by a smooth positive definite matrix function, symmetric matrix. All right. Is that clear?
I see.
Yeah. Okay. So G is, it follows from this that G is going to be smooth and G is going to be positive definite and symmetric, right? So G of P is positive definite and, well, symmetric is obvious because Gij is G of del del xi del del xj. Okay. All right. Okay, so this matrix G of the, this is the called the matrix of the Riemannian metric. This is positive definite and symmetric, right? For all P in the domain of the chart. Okay. Yes. So let me, before proceeding, let's look at some things we can do once we have a Riemannian metric. So okay. So suppose we have a Riemannian metric, right? So it's given by sum over ij, Gij dxi tensor dxj. This matrix Gij is positive definite. Okay. And now what we can do is we can measure lengths of tangent vectors, right? So we're just going to write inner product VW for GP of VW, okay, if VW are vectors in TPM, and we will write norm of V for GP of VV to the power half, okay. So then we can define the length of a curve in M by the usual formula. If gamma is a piecewise C1 curve in M, then you define the length of gamma to be the integral from A to B of norm of gamma prime T dt, okay. And notice that the length is invariant under reparametrization. So if I reparametrize gamma to be defined on an interval CD by taking a C1 diffeomorphism sigma from the interval CD to the interval AB, and I look at the reparametrized curve gamma composed with sigma, then gamma composed with sigma prime by the chain rule, this is gamma prime of sigma T into sigma prime T. And so what will the length of gamma composed with sigma be? This will be by definition the integral from C to D of the norm of gamma composed sigma prime T. That's going to be norm of gamma prime composed sigma T into the absolute value of sigma prime T. Now I make the change of variables S equal to sigma T. Then this integral by the change of variable formula becomes the integral from A to B of norm gamma prime S ds, right? That's just by the change of variable formula. And so that is the length of gamma, okay? So the length is invariant under reparametrization, okay? Is this all right? Yes? Yes?
Yes, sir.
Okay, so once the length is invariant under reparametrization, you can always parametrize your curve by what's called arc length. So arc length parametrization . So suppose you have gamma from AB into M, C1 or piecewise C1 curve. Okay. Then you define a function S of t to be the length of gamma restricted to the interval A to T. Okay. T in AB. Okay. So then S maps the interval AB to the interval 0, L, where L is equal to the length of gamma, right? Yes? Right? And S is monotone increasing, right? This length is going to be monotone increasing. And notice that, so what is my picture? I have basically the interval AB here. And I have this S, which is mapping to the interval 0L. And I have gamma, which is mapping into M. Yeah. Now, gamma may not be 1-to-1. Okay. So gamma induces an equivalence relation on the interval AB, where 2 points T1, T2 are equivalent if gamma T1 is equal to gamma T2, right? This is an equivalence relation induced by gamma. Okay. And the point is that this length function S, this respects this equivalence relation. So if S of T1 is equal to S of T2, right? Where T1 is less than T2, then what does that mean? That means that the integral from T1 to T2 of norm gamma prime T dt is 0, right? So that means that norm gamma prime T is 0 in the interval T1 to T2. And that means that gamma T1 is equal to gamma T2, right? Yes? Okay. So actually, I was saying it the wrong way around. This gamma respects the equivalence relation induced by S, right? S is a monotone increasing function, a continuous monotone increasing function. So it induces this is a quotient map from AB to 0L. This is a quotient map. Gamma respects this quotient relation, right? If ST1 is equal to ST2, then gamma T1 is equal to gamma T2. Then by the fundamental property of quotient spaces, this means that gamma induces a map from 0L into M, gamma tilde, right? Is that clear? Yes?
Yes, sir.
So there exists a unique map, gamma tilde, from 0L to M, such that gamma is equal to gamma tilde composed with S. Okay. So this gamma tilde is called the arc length parametrization of gamma. Because it satisfies that the length of gamma tilde on an interval S1, S2 is equal to S2 minus S1. Okay. So its speed, which is the norm of gamma tilde prime, this is constant equal to 1. Okay. So I leave it as an exercise to you to show that this gamma tilde is C1 also. Okay. So this gamma tilde is C1. Okay. All right. So you can always parameterize a curve if it's non-constant. I mean, if it's constant, then this length of gamma will be 0. So then this S, I mean, it just takes values and it maps to the singleton 0. So fine, you just have a curve defined on a point. So that's not so interesting. But if it's non-constant, you can always get an arc length parameterization like this. Okay. Okay. So now once we can define lengths of curves, we can define a distance function, right? So remember, in Euclidean space, your distance function, the distance between 2 points in Rn is the length of the straight line joining them. And that length is the shortest length, right, of all curves joining the 2 points in Rn, right? The shortest curve between 2 points in Rn is a straight line, right? So this suggests that in a Riemannian manifold, we can define a distance by taking the shortest length of curves joining any 2 points, right? So in other words, you define the distance between points PQ to be the infimum of the length of gamma, where gamma is a piecewise C1 curve from P to Q, okay? So you take all piecewise C1 curves from P to Q, take their lengths and take the infimum. Then the claim is that this is a metric, okay? So let's quickly check that this is a metric. So first of all, this is symmetric, dpq equal to dqp, because if I take any curve from P to Q, I can just reverse it. That will give me a curve from Q to P, which has the same length, right? I look at the curve gamma bar of T is gamma of A plus B minus T, right? So that goes from Q to P, and these have the same length. So when you take infimums, you'll get the same infimum, okay? So this distance function is symmetric. Now it satisfies the triangle inequality. So if I take 3 points PQR, I have to show the triangle inequality. So how do we do this? So since the distance is an infimum, given an epsilon positive, we can choose a curve alpha from P to Q and a curve beta from Q to R, such that the length of alpha is less than or equal to distance PQ plus epsilon, and the length of beta is less than or equal to distance QR plus epsilon. Then you concatenate these two curves. The curve alpha dot beta goes from P to R, and its length is just the sum of the lengths of alpha and the length of beta. So that is going to be less than distance PQ plus distance QR plus 2 epsilon. So therefore, since the distance between P and R is the infimum of lengths of curves, and alpha dot beta is a curve from P to R, that means the distance between PR is going to be less than or equal to distance PQ plus distance QR plus 2 epsilon for all epsilon positive. Now you let epsilon tend to 0 and you get the triangle inequality. Is this okay? Yes?
Yes, sir.
Okay, so the last thing now to check is positivity, right? That is, if PQ are distinct points, then the distance PQ is positive. So how do we do this? So first we choose a chart U comma phi near P, such that Q is outside the closure of U. And let's suppose that the image of this chart under phi is the ball of radius 2 around the origin in Rn. Okay, we can always do this. And you let V be the inverse image of the ball of radius 1 around the origin. Okay, so V closure is going to be contained in U. Assume that phi of P is 0. Okay, this chart maps P to the origin. Now look at my Riemannian metric. So the matrix of the Riemannian metric G, this matrix Gij, this is going to be a smooth matrix valued function from U to MNR. So it's in particular, it's continuous with values in symmetric positive definite matrices. And now if I take this V here, V closure is a compact subset of U. So on this compact subset, if I look at the function, so I look at a function of pairs P comma V, where P is in V closure and V is a unit vector in Rn. Okay, so in other words, I'm looking at V closure cross Sn minus 1, the product space that is compact. On that compact space, I have a continuous positive function. P comma V goes to inner product between GPV comma V, Euclidean inner product. So since this is positive and continuous on a compact set, it attains its infimum, right? So this infimum is going to be therefore some positive number, epsilon naught squared, okay? All right. So now, if I take any curve gamma from P to Q, say gamma is defined on the interval 0, 1, then since Q lies outside my chart U, there is going to be some time where gamma of T is outside V, let's say. So let T naught be the infimum of T such that gamma T is not in V. Okay. So this is the first time you go outside the ball V. Okay. So then it's easy to show that gamma T naught belongs to the boundary of V. Okay. And by definition of T naught, up to time T naught, you're contained inside V closure. Okay. So gamma of closed interval 0 T naught is contained in V closure. So let gamma tilde be the image of gamma under the chart. So let this be phi of gamma restricted to 0 T naught. Then gamma tilde of 0 is 0. Gamma tilde of T naught, this belongs to the unit sphere, because V, remember, was the inverse image of the unit ball. So phi of V is the unit ball, and phi of boundary V is the unit sphere, Sn minus 1. Okay. And gamma tilde of the closed interval 0 to T naught is contained in the closed unit ball in Rn. So if gamma tilde of T has coordinates x1t to xnt, then gamma prime T is what? Summation xi prime T del del xi. So what will norm gamma prime T squared be? This is inner product of gamma prime with gamma prime. So it's going to be sum over ij, gij of gamma T, xi prime T, xj prime T, right? And this is nothing but the Euclidean inner product between capital G of gamma T into gamma tilde prime T, inner product with gamma tilde prime T. Okay. Now, if I divide by norm of gamma tilde prime T squared and multiply that by that, then I'll get G acting on a unit vector, inner product with a unit vector. So this is going to be greater than or equal to epsilon naught squared into norm of gamma tilde prime T whole squared, right? Okay. And therefore, the length of gamma, that is greater than or equal to the length of gamma on the interval 0 to T naught. And there, gamma, the norm of gamma prime is greater than or equal to epsilon naught, the norm of gamma tilde prime, Euclidean norm of gamma tilde prime. So this is going to be greater than or equal to integral from 0 to T naught, epsilon naught, Euclidean norm of gamma tilde prime. And now for the Euclidean norm, this by the triangle inequality for integrals, this is going to be greater than or equal to epsilon naught times the norm of the integral of gamma tilde prime from 0 to T naught. And that, by the fundamental theorem of calculus, is gamma tilde prime, gamma tilde T naught minus gamma tilde 0. And now we can use the fact that gamma tilde T naught belongs to the unit sphere. So, and gamma tilde 0 is 0. So this difference has norm 1. So this becomes just epsilon naught. That means that the length of gamma is greater than or equal to this fixed constant epsilon naught for all curves gamma from P to Q. Therefore, the distance between PQ, which is the infimum, is greater than or equal to epsilon naught, which is positive. Okay? Is that clear?
Yes, sir.
Okay. So we get a metric on our manifold M. Okay. So there are some natural questions which we'll give some answers to later. So given 2 points P, Q, and M, does there exist a curve gamma from P to Q which whose length is equal to the distance between PQ? In other words, is the shortest length attained, right? Is there a curve which attains the shortest length? And if so, how can we characterize the length minimizing curves? Okay. So just one small comment. Yeah. Any smooth manifold admits a Riemannian metric. So here, if you take, you can do this using partition of unity. You take charts, you take a cover of the manifold by charts, which is locally finite. And then you take a partition of unity subordinate to this cover. Then you take G naught is the Euclidean metric on Rn. And then what you do is, for each chart Ui, you look at the pullback of the Euclidean metric by phi I star, by phi I. Okay. So see, this G naught is the usual Euclidean inner product on each tangent space of Rn. So I can pull back by the derivative of the chart, right? Pointwise, to get pointwise a inner product on each tangent space, right? Now that is defined inside the chart, but I want to extend it to something global. So then I multiply by my cutoff function psi I. So this vanishes, its support is contained inside Ui. So this, when I multiply by this, I'll get a globally defined section of the tensor product of the cotangent bundle with itself, right, of T star m squared, yeah, which is 0, whose support is contained inside Ui. Then I sum over I. Okay. Okay, see the support of psi I times phi I star G naught. This is contained in Ui. Okay. So this is smooth on all of n. And the sum above is locally finite because my covering is locally finite. So at any point, there are only finitely many I such that the point P belongs to Ui. So at any point, this sum is finite. So there's no issue of convergence. So therefore, this G that I get, this is called a 2 tensor. That means a section of the second tensor product of the cotangent bundle. This is a smooth 2 tensor. All I have to check, and it's symmetric because the pullbacks of these symmetric tensors are symmetric. I just have to check it's positive definite at each point. So if I take any point P, then there exists, because I have a partition of unity, my summation psi I is equal to 1, right? So at the point P, there's going to be some I such that psi I of P is positive, right? Okay. And so therefore, GP of VV for any vector V in TPM, which is non-zero, will be greater than or equal to psi I of P into phi star G naught of VV. And both of these are positive, so the product is positive. And so G of VV is positive. So therefore, it's an inner product. Okay. Yeah. The point is, these, when I add up these bilinear functions are positive semi-definite. Okay. And at each point, one of them is, at least one of them is positive definite, strictly positive definite. Therefore, the sum will be positive definite. Okay. Is it clear?
Yes, sir.
Okay. So therefore, any smooth manifold admits a Riemannian metric. So having a Riemannian metric is not a restrictive condition. Any manifold becomes a Riemannian manifold. Okay, it has a Riemannian metric, and so you can make it a metric space also, right? By defining the distance as we did earlier. Okay. So the main example is one motivating example is you take submanifolds of Rn. These will be Riemannian manifolds with a metric called the induced metric. So what is a submanifold of Rn? So it's a subset of Rn such that you have a family of open sets Ui in Rn which cover M, okay? And for each I, you have a diffeomorphism phi I from this open subset Ui in Rn to another open subset Vi in Rn, okay? Such that phi I of Ui intersect M is Vi intersect R little n cross 0. Okay, so let me just draw you a picture so that you see. So yeah, so okay, so submanifolds of R capital N as Riemannian manifolds. So what is a submanifold? It means you have a subset. Could look something like this. Such that if I take any point, I have a cover by open sets in Rn. So I have some U here. Okay, and I have this is a open in R capital N. So I have this M, this is a subset of R capital N. And I have a diffeomorphism phi. To some subset V in Rn, R capital N, such that this portion of the manifold, I can straighten it out. It maps to a lower dimensional Euclidean space, okay, cross the zero vector. So this thing is V, this is open. V is phi of U. Okay. And this thing here is going to be the image of this part here. So this part here is U intersect M. This maps to a straight piece here, which is V intersect R little n cross zero vector of size n minus n. Okay. Is this clear? So this is a linear subspace of R capital N. Okay. So this is equal to phi of U intersect M. Okay. Is this clear? Yes. Okay.
Yes, sir, it is clear.
Yeah. So it follows that this M becomes a manifold. Where, so this UI together with phi I restricted to U intersect M, this gives me charts on M, right? Okay. All you have to check is that the change of charts is smooth. So that you can do. I'll leave it to you to check that. Okay. So this gives charts on M. So M is also an N manifold. Okay. So M is an N manifold. And the inclusion I from M into R capital N. This is a smooth map. Okay. And the derivative of this inclusion map, which goes from TPM to Rn, R capital N, this you can show is injective for all N or for all P in M. So this is explained in the notes, but I leave it to you as an exercise if you want to try. Okay. Yeah. So that means that TPN, the tangent space at each point, this is identified with a subspace of Rn. Okay. A linear subspace. Okay. So in this picture, this would be this linear subspace. Okay. This would be TPM sitting inside Rn. Okay. All right. So for a submanifold of Rn, the tangent space is identified with the subspace of Rn at each point. So what we can do is we can restrict the Euclidean inner product on each. So the Euclidean inner product on R capital N to each tangent space TPN. Okay. And this will give, you can check that this gives a smooth Riemannian metric. G on M. Okay. Which is called the induced metric. Because it's induced from the Euclidean metric. Okay. Is this clear? Yes.
Yes, sir, it is clear.
Okay. Now, so in this case, for gamma, which is a curve mapping into M, which is sitting inside Rn, right? We have gamma prime T. And this is I can take this to be the usual derivative of a curve in Rn. This is just a curve in Rn, right? And the length of gamma for the induced metric is just the usual length in Rn. Okay. Right? Okay. Length of gamma is equal to integral A to B norm gamma prime T dt, where this norm is the Euclidean norm, right? Is this clear? Yeah.
Yes, sir.
Okay. All right. So now suppose, so fix PQ in M. Suppose gamma is a, so okay, let me take a C2 curve such that a C2 curve from P to Q of minimum length. Okay. So the length of gamma is the distance between PQ. Okay. Then we want to say that gamma satisfies a certain equation, which will be called the geodesic equation. So there's just a minute left, but we're going to derive this geodesic equation that gamma satisfies. So I won't do it now because there's just a minute left. Let me stop this session and start a new one. Okay. Yeah. Okay. All right. So let's derive this geodesic equation, which any length minimizing curve has to satisfy. Okay, so say we have, this is our manifold sitting inside Rn, and we have a curve gamma. Okay. Then what I can do is I can take any one parameter family of curves keeping the endpoints fixed. Okay. So let F from the interval AB cross minus epsilon epsilon into M be C2 map, okay, such that if gamma S of T is okay, let me change the gamma T of S. So if gamma T of S is F of ST, so S belongs to AB, T belongs to minus epsilon epsilon. Okay. Then we assume that gamma 0 is equal to gamma, and gamma T of A is equal to gamma of A, gamma T of B is equal to gamma of B for all T less than epsilon. Okay. So then we define, so this family of curves is called a variation of gamma. It's called a proper variation of gamma because the endpoints are fixed. Okay. So any variation means a one parameter family of curves at which at time 0 is equal to gamma. And the variation is called proper if the endpoints are the same as the endpoints of gamma throughout the variation. Okay. So then for this proper variation, we can define the variation vector field capital V of t. This is going to be, sorry, V of S, capital V of S. This is going to be del del t at t equal to 0 of gamma t of S. Okay. So if I fix S and I vary t, then I get a curve in M which passes through gamma of S at time t equal to 0. So when I differentiate with respect to t at time t equal to 0, I'm going to get an element of the tangent space to M at the point gamma S, right? So this is a vector field along gamma, right? So V is a vector field along gamma. Okay. Is that clear? Yes. Okay. Now, without loss of generality, assume that gamma is parametrized by arc length. Okay. So we can assume the norm of gamma prime is, say, constant 1. Okay. Because we know that the length is invariant under reparametrization. So we can always choose the arc length parametrization. Okay. Yes. All right. Okay.
Yes.
Now, what do we have? Now we know that if I look at the length of gamma t, this is greater than or equal to length gamma for all t in minus epsilon to epsilon. And length of gamma 0 is equal to length of gamma. You have equality when t is equal to 0. That means as a function of t, this length of gamma t, it has a minimum at t equal to 0. Therefore, its derivative at time 0 is 0, right? So 0 will be equal to ddt at t equal to 0 of length of gamma t. This is ddt at t equal to 0 of integral from a to b inner product so let me write it in this form. So it's the norm of the tangent vector. The tangent vector is del f del s. Okay. So inner product del f del s, del f del s, okay, to the power half ds, right? Okay. Yes. Now, what can I do? I can differentiate under the integral sign. So then this will become integral a to b del del t of del del t at t equal to 0 of this inner product del f del s to the power half, right? Now, this will become, by the chain rule, half times. So this del f del s at t equal to 0, del f del s at t equal to 0 to the power minus half. This thing is equal to 1 because this is norm gamma prime to the minus half, which is 1. Okay. Into, now I have to differentiate the inner product, right? But because the inner product is bilinear, this is going to be the inner product between del del t of del f del s, inner product with del f del s, plus inner product del f del s, del del t of del f del s, right? Yes, by the Leibniz rule. So this will be, because it's just the Euclidean inner product, right? This is just the Euclidean inner product. So this is going to be twice del del t at t equal to 0 of del f del s, del f del s ds, right? Is this clear? Yes?
Yes, yes.
Yes, sir.
Right. So, okay. Yeah, I mean, see, if I have two vector fields along gamma, right, they're taking values in R capital N, right? So in R capital N, let's say the vector fields are V and W. So if V has coordinates in R capital N, V1 up to V capital N, and W has coordinates W1 up to W capital N, then inner product VW is what? Summation VI WI? It's just a Euclidean inner product, right? So it's summation VI WI. So when I differentiate that, what will I get? Summation VI prime WI plus summation VI WI prime. Now the first term is inner product of dV dt with W, and the second term is inner product of V with dW dt, right? Just the usual derivative in Rn. Okay. Is that clear? Yeah. Okay. So I get this. Now I can use the fact that f is C2. So the these partial derivatives commute. So I can take the del del t inside. Okay. So if I take the del del t inside, what is del f del t at t equal to 0? By definition, that is my variation vector field V, right? So then this is going to be del V del S inner product del f del S, right? And this half and the 2 will cancel. So what I'm left with is integral A to B. So del V del S, I can just write as V prime S. And then this del f del S at time t equal to 0. This is at time t equal to 0. This is going to be gamma prime S, right? Is this clear? Yes?
Sir. Yes.
Now this I can write as, again by the Leibniz rule for the Euclidean inner product, I can write this as DDS of the inner product of V with gamma prime, right? So if I do this, then I'm going to get two terms. By the Leibniz rule, it will be inner product of V prime with gamma prime, plus I'll get V inner product with gamma double prime, right? So I have to subtract that. So I'll get a minus inner product of V with gamma double prime, right? DS. Okay. Is that clear?
Yes, sir.
Now, by the fundamental theorem of calculus, the first term is going to be what? It's just going to be V inner product gamma prime evaluated at AB. And then I'll have minus the integral AB V gamma double prime. Okay. But the first term is 0 because V of A and V of B are both 0, right? Because all of the curves gamma t have fixed endpoints P and Q, right? Okay, because gamma t of A is P for all t. So when I take ddt, I'll get 0 at time 0, right? And gamma t of B is Q for all t. Is this clear? So this boundary term vanishes. What we've done here is nothing but an integration by parts, right? This is just an integration by parts. Is that clear?
Yes, sir.
Now, the last step is to notice that since V is tangent to the manifold M, this Euclidean inner product with gamma double prime is the same as the Euclidean inner product with, so what we can do is, since TPM is a direct subspace, is a subspace of Rn, we can write R capital N as TPM direct sum its orthogonal complement, right? And any vector V I can write as a tangential component plus a normal component. Okay, where the tangential component belongs to TPM and the normal component belongs to TPM perp. Okay, so now if the vector V belongs to TPM, then the inner product with gamma double prime is just going to be the inner product with the tangential component, right? Because the inner product with the normal component will vanish. Is that clear? Yes?
Yes, sir.
So what does this mean? This implies that the integral A to B of the inner product of V. So this last part is because V of S belongs to T gamma S of M for all S. So therefore I can replace gamma double prime by its tangential component. So this implies that V inner product with the tangential component of gamma double prime, this is 0. And this is true for all vector fields actually V along gamma, such that VA equal to VB equal to 0. Why is that? So there's just one little comment to make there, that given such a V can construct F of ST equal to, what you have to do is basically you take a projection, you take basically gamma of S plus T times V of S. Okay. And then you project this to the manifold where pi is a smooth projection to this is from a neighborhood say U containing M. To M. This is a projection. So such a projection exists by something called the tubular neighborhood theorem, but I won't go into that. So you can define such a variation, right? You can construct this variation such that its variation vector field is equal to V. Okay, so del F del T at T equal to 0 is equal to V. Okay, so given any vector field V along gamma, which vanishes at A and B, you can construct a proper variation like this. And then you apply this argument, and you finally get that the integral of inner product V between the tangential component of gamma double prime is 0. So since this is true for all V, a standard argument will tell you then that gamma double prime tangential component is identically 0. Okay. And this last equation, this is the geodesic equation. This is the geodesic equation. Okay. So we see that a shortest length curve, well, in Rn, a shortest length curve was a straight line, right? And a straight line in Rn can be described as one whose second derivative is 0. Its acceleration, gamma double prime, is 0, right? That is equivalent to gamma being a straight line in Rn, right? Now, in a manifold sitting inside Rn with the induced metric, what we're finding is that a shortest length curve, it has to satisfy also in a certain sense, its acceleration is 0, where now, how do we get the acceleration of a curve in M? So what we do is, we have our manifold M sitting inside Rn, right? So how do you get an acceleration of a curve? Well, you look at the curve, you look at the tangent vector to it. Now the tangent vector is taking values in the tangent space to M, right? But when I take the second derivative, so if I have a curve gamma inside M, say a C2 curve, right? So M is sitting inside R capital N. So then gamma prime at each point, this belongs to the tangent space to M at gamma T. But gamma double prime, if I take the second derivative, this is just a vector in R capital N, right? So if I want an acceleration which is a vector in M, what I need to do is take the tangential component. That will again give me a tangent vector in M, right? Okay. So that is our acceleration will be the tangential component. Right? This will again be a tangent vector to M. This is the acceleration of gamma. So okay, you just take the tangential component of the usual acceleration in Rn, right? Is that clear? And what we're finding is a geodesic has to have 0 acceleration in M. Okay. Is that clear? Geodesic meaning a shortest length curve has to have a 0 acceleration. So a geodesic will be a curve whose acceleration is 0. A geodesic will be defined to be a curve whose acceleration is 0. So let me give you an example of such a curve. So example, if you take say S2, the 2 sphere, right? Then if I take the equator, for example, right? So gamma T is cos t sin t 0 in S2, which is my n sitting inside R3, right? Then gamma double prime, this is minus gamma, right? If I differentiate twice, I'll just get minus gamma, right? Yes. And minus gamma, this is perpendicular to the tangent space to S2, right? At gamma. At any point, so the acceleration is going to be, it's your physics, it's the, what do you call it, centrifugal or centripetal force, right? It points, when you move in a circle, the acceleration points towards the center of the circle, right? Yes? So this is normal to the tangent space, right? This is normal to the tangent space. So that means that your acceleration, gamma tangential component is 0. Okay? Is that clear? Yes?
Yes, yes.
Okay, so this is a geodesic in the two sphere. More generally, if you take any rotation of this, that will also give you a geodesic, right? So rotation of this means basically you'll get what's called a great circle, right? So the great circles are geodesics in the two sphere. Great circle means the intersection of a plane with S2. So great circle, C is a plane through the origin, intersect S2. Okay, this is a geodesic. Okay. So any great circle is a geodesic. Is this clear? Right? Yeah, in the great circle, the acceleration will always point towards the center. So the tangential, and this is normal to the tangent plane. So the tangential component will be 0. So this will be a geodesic. Is this clear?
Yes, sir.
Yeah. Okay. So this is a simple example of geodesics. So a geodesic means the normal component of the acceleration, the tangential component of the acceleration is 0. In other words, the acceleration is only normal to the manifold. Okay. Any acceleration is only in the normal direction. Okay. Yeah. Any acceleration is only in the normal direction. Okay. So this suggests then a way of a natural definition for covariant derivative, right? If I have, so covariant derivative, so suppose gamma is a curve in M and V is a vector field along gamma, right? So then we want to define the covariant derivative d capital dV dt. What can we define this to be? What can we define this to be? Well, you just take the usual derivative. That will give you a vector in Rn, and then you take its tangential component, right? Got it? Is it clear?
Yes, sir.
Okay, and so this suggests a connection on the tangent bundle so if I have a vector field, say X is a vector field on M, right? So then I can think of X as a map from my manifold sitting inside Rn. So, well, I can think of it as a map taking values in Rn, right? This is a smooth map because X of P, this belongs to TPM, which I am identifying with a subspace of Rn, right? Okay, so I can think of X as a map taking values in Rn, right? Yes. So then, if I want to define, my connection, if I take a V in TPM, right, how will I define the covariant derivative nabla sub V of X, right? So I can define this as follows. I just take ddt at t equal to 0 of X of gamma t. So this will give me a vector in R capital N, and then I take the tangential component, okay, where gamma is any curve such that gamma 0 is P, gamma prime 0 is V. Okay. Make sense? Yes. Now, what is this? This is nothing but, by the chain rule, this is nothing but the derivative of X at P acting on V. And then I take its tangential component, right? Where since X is a map from M into Rn, its derivative dx at P, this I can think of as a map from TPM, a linear map from TPM to R capital N, right? Is this clear? Yes? Okay. So my connection on TM, this will be a map nabla from chi-m cross gamma TM, which this is again nothing but just chi-m, to gamma TM, right? This is again nothing but just chi-m, sorry. This will be xy goes to nabla xy. This is defined to be what? You take the derivative of y, let it act on the vector field x, that gives you a vector in R capital N, and then take the tangential component. That's it. This is your connection. Is it clear?
Yeah, this is clear.
Okay, this is clear. Okay, good. So this connection it satisfies two properties. This connection satisfies so one, this property is called metric compatibility. So for all x, y, z vector fields on M, X applied to the inner product between Y and Z is equal to the inner product between nabla XY and Z plus the inner product between Y and nabla XZ. Okay. So the proof of this is simple because the inner product with respect to the induced metric on the manifold is just the same as the inner product in Rn, right? The Euclidean inner product. So this will follow from this. The proof is very simple. It's just if say gamma is an integral curve of X, right? So then X applied to inner product YZ, this is ddt at t equal to 0 of inner product Y gamma t and Z gamma t, right? And now this thing is the same as the Euclidean inner product, right? So for the Euclidean inner product, I know that I have the Leibniz rule, right? So this is going to be the inner product between ddt at t equal to 0 Y gamma t with Z plus Y inner product ddt at t equal to 0 Z gamma t, right? But now, because Z is tangent to the manifold, this inner product is the same as the inner product of the tangential component with Z, right? Yes? Because the inner product with the normal component vanishes, right? Because Z is tangent to the manifold. Is that clear? Similarly, over here, because Y is tangent to the manifold, this inner product is the same as the inner product with the tangential component, right? Is that clear? Okay, so this is because YZ are tangent to the manifold. Is that clear? Yes?
Yes, sir.
Yes, sir.
It's okay? Yes, thank you. Okay, yeah. So what is this? This is by definition, this is nabla XY. And the other one is nabla XZ. Okay, that's it. So is it clear? So this will satisfy this metric compatibility. Okay. And there's another property which it satisfies, which I won't prove. This is called symmetry. That nabla XY minus nabla YX is equal to the bracket of XY. Okay. All right. So this is what, so this connection is called the induced connection from the induced metric. Okay. Then, so this satisfies symmetry and metric compatibility. So to finish, let me just state what's called the fundamental theorem of Riemannian geometry. So for a general manifold, there exists a unique connection on the tangent bundle satisfying symmetry and metric compatibility. Okay, so this connection exists and is unique and is called the Riemannian connection or the Levi-Civita connection. Okay, so let me stop here. There's less than a minute and we'll continue next on Friday. Okay. All right, so I'll see you Friday. Let me stop here.